Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this topic on chemistry of transition elements. So this is topic 28 for the CIE specification, so this is the Cambridge Internationals. So if you are studying the CIE specification, then this is, well, you've come to the right place basically. So obviously this is looking just at topic 28 in particular. Obviously with CIE there's loads of different topics spanning from year 1 to year 2, and the full range of videos for year 1 and year 2 are available on Allery Chemistry YouTube channel. Hit the subscribe button just to show your support for this project. That'll be absolutely brilliant. Plus any of this information here, so these are just slides, they are available to purchase, which are great for your revision, so you can put them in your file and write notes, all of them if you wish. They are available to purchase. If you click on the link in the description box below, you'll be able to get a hold of them there. Like I say, they're great value for money, and I've kind of bundled all of these up into kind of bigger bundles of topics, so you can get the full year 1 and year 2 specification if you wish. So this is quite a big topic. This is probably one of the biggest ones in CIE. So there's a lot of information here. Basically, it's kind of the main and only topic that looks into transition elements. So some of this might be fairly new, but I'm going to bridge quite a lot of this with some previous topics as well. But it is important that you have a good understanding of orbitals and electrons obviously moving into different orbitals as well, and obviously that you would have learned in year 1 chemistry. So I'm going to be bringing some of this stuff back in for this here. So the best place to start with this topic is D block elements. So obviously we need to know where these D block elements are in the periodic table, and we can see we've got the periodic table that's up in front of us there. The D block elements actually sit in the middle of the periodic table, so that's this kind of block here. And to be honest, a lot of the chemistry we've been looking at, to be honest, is mainly being kind of to the left and right of this block. We don't really do a lot with it, but it actually has its own topic where we just look at these chemicals here, some of these elements in the middle. So some of these elements are transition metals, not all of them. Okay, so the ones that we're really going to look at here are the ones in the top row. We're not really going to look too much at the ones below that. So this is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So that's these ones at on the top row there. So let's have a look at some electron configurations. So a transition element is a D block element that can form at least one stable ion with a partially filled or incomplete D subshell. Okay, don't get them mixed up. There's difference between D block elements and transition elements. Okay, so transition element is a type of D block element. So the D subshell, as you'll probably remember from year 1 chemistry, can hold up to 10 electrons in total. And for period 4 D block elements, only 8 of these are transition elements. So scandium and zinc, which are at the extreme ends of that kind of top row of the transition elements, of the D block elements, are not transition elements. And this is because they don't form stable ions with a partially filled D subshell. So we'll kind of have a look at that a little bit later on. So let's have a look at the electron configurations of the 8 transition elements in period 4. And what you'll see here, and this is again, you would have seen this in year 1, but we fill up these orbitals singly first, and then we double up after that. Okay, remember these electrons don't want to be sitting in the same orbital as each other. They want to kind of be as far apart as they can be. And they will only doubly occupy if they have to. There is no other option for them. So let's have a look. So all of these have the electron configuration of argon. Okay, so that's what that means. They're all an AR with a square bracket. You might see that sometimes with transition metals. Instead of writing 1s2, 2s2, 2p6 and writing all that stuff before, we just say, right, the electron configuration of argon plus what we're going to show down here. Okay. So there we are. Okay, so there we are. That's the electrical configuration of argon. So titanium is the first one. So it has 4s2, and it has 2 in the 3D orbital. So this is partially filled 3D orbital, so it's definitely a transition element. Vanadium has 3. Chromium has 5. Now what happens here is one of the electrons from here jumps into this one to occupy a full half shell. This is more stable than keeping 2 paired up in here. Remember, these electrons want an opportunity, if they can, to occupy an orbital singly, as long as the overall energy is favourable. And then with manganese, the extra electron then goes in here, okay, into the 4s. It's more energetically favourable to double up in this orbital before we fill up here. Iron, we then have to double up. We don't have a choice. Cobalt and nickel, they obviously double up there. And then again for the last one here, copper, we have a full D subshell, but we have a partially filled S subshell. So the electron from here then jumps into here. This is more stable to have a full D subshell here, and this one is obviously left unoccupied here. Okay, so chromium and copper, so these behave slightly differently, as you can see. So an electron from the 4s orbital moves into the 3D orbital to create a more stable half full or full 3D subshell respectively. So that's what we're talking about there. So the electron here went into there, and then this electron here jumped into this orbital here. Okay, so that's what happened. So basically, just remember these two in particular, chromium and copper. Okay, which is down here. Okay, so just remember these two in particular. Their orbitals, or when you're filling the electrons up, the atom, or the element should I say, has this full or half 3D subshell and a full 3D subshell for copper. So just make sure you're aware of that. Do not write that, otherwise you are going to get that incorrect. You're going to get that wrong. Okay. So scandium and zinc, as we kind of isolated these before, these are not transition elements, and we need to understand why. Okay, so scandium only forms one stable ion, okay, and that's scandium 3+, Sc3+. Now that scandium 3+ has an empty D subshell, and because it's empty, it's not partially filled, it's not a transition element. So there's scandium as an element. Okay, now remember, you're looking at that thinking, but it's got a partially filled D subshell. Remember, what makes something a transition element is the stable ion that it forms. It must form a stable ion, at least one stable ion, that has a partially filled D subshell. This is not an ion, this is an element. And the only stable ion it does form is scandium 3+. And you can see here, there is no electrons at all in the 3D subshell. Now it's the same with zinc. Zinc only forms one stable ion, which is zinc 2+, and this has a full D subshell. So because it's not partially filled, it is not a transition element. So here's zinc as a metal, and here's zinc as an ion. Now, when we remove electrons, as you'll see in a moment, we actually remove from the 4s orbital first, then we start dipping into the 3D. So this has obviously lost its 2 electrons in the s orbital. It's got a full 3D subshell, and so therefore there is no... well, it's not a transition element. This is not partially filled. So that's the reasons why. Okay, so let's kind of carry on looking at electron configuration of transition metals. So transition metals, they lose electrons in a very specific way, as I kind of just hinted at just before. So let's look at the electron configuration for Fe3+ first. So what it actually does is it loses 3 electrons, 2 from the 4s and 1 from the 3D. Okay, now all becomes quite apparent when we can see this here. So you can see there's the electron configuration there, okay, which has got 4s2. And then what's going to happen is we're going to remove the electrons to form Fe3+. So there we go, that goes. And then if you see it up here, that should disappear. It should do. No, not yet. It will do in a moment. So you'll see here, this is the electron configuration. So the 4s electrons have been removed. Then we remove the 3rd electron from the d orbital, and obviously that should give 23, which matches, and there it is. So we lose from the 4s first, and then the 3d. There we are, and then the 3d there. So that's what we should have, is this kind of setup here. Okay, so always when you're removing electrons from a transition metal, you remove from the 4s first, then you start dipping into the 3D, and you remove them singly first. So you try and leave singly occupied orbitals if you can. Okay, right. So let's have a look at some properties of transition metals first. Okay, so transition metals have very specific properties. They include variable oxidation states. They form coloured ion solutions. They're good catalysts as well, and they can actually form complexes too. Okay, so you've got various different properties here. Now, what we're going to do, really, a lot of this topic is exploring these properties and looking at the different reactions and what they can do, because actually, out of all the areas of chemistry, although it's not kind of the biggest, organic chemistry is probably the biggest area of chemistry in total, but although inorganic chemistry, which this kind of sits into, is not a big area, it's probably the nicest one because it's colourful. There's loads of colours there. The metals that we see there are used widely in terms of jewellery, in terms of catalysts, in terms of the paints that we see, the colours that we see, for example. All of these are absolutely vital, and obviously we have transition metals in our blood, iron for example, and because iron's a transition metal, it allows us to survive. So they are, obviously any area of chemistry is vital, of course we're going to say that, but this is it's quite a specialised area of chemistry, I would say. So transition metals. So transition metals have variable oxidation states. That's one of the properties of them, and throughout this video we're going to look at all of them. But variable oxidation states, and this is because the electrons sit in that 4s and 3d energy levels. And as we'd seen in the diagram just before, these are very close. They sit very close to each other. And because their energy levels are quite close, the electrons can kind of jump from 4s to 3d quite readily, as we've just seen before when we're removing the electrons. So as a result, electrons are gained and lost with a pretty much similar amount of energy when they form these ions. And obviously we can see here we've got all of the elements kind of listed in this table here, and the ions that they form. And you can see obviously scandium only forms one ion, which you can see here. So obviously we've seen scandium. That isn't a transition element. Remember, I've just put it on there just for reference really. But some of them have quite a few. So vanadium, chromium, manganese, iron, cobalt, nickel, copper and titanium. Now you can see here these are the oxidation states along the left hand side here. You would have seen that in the electrochemistry topic in year 1 when you looked at oxidation states. So if you're not familiar with that, please go back and have a look at that. It's really important. But transition metals can have varying oxidation states, and that makes them quite versatile. So what we can do is we can predict the maximum oxidation number for a transition element, or we can predict the maximum oxidation number for a transition element. It's basically the number of 4s electrons plus the number of unpaired 3d electrons, and this pattern is only broken by copper. So that's the way in which we can try and predict what they are. And obviously they also form coloured ions in solution. And we'll look at some of these colours as well. There's loads of different colours here that you may have seen. So you might recognise some of these, like say from practical work. So vanadium 2+ is a lovely violet colour. Vanadium 3+ is green. Vanadium 4 or VO2+ is blue. VO2+ is yellow, so that's vanadium 5+. Chromium is green or violet colour, so it's violet when it's surrounded by 6 water ligands, and we'll look at ligands later on. But they're normally substituted, so they look actually green when you do it. Dichromate is orange. Again, you might have seen these in the alcohols topic, so the hydroxy group topic. Manganese Mn2+, MnO4 2- is green, and MnO4- is purple. Iron 2+ is pale green. Iron 3+ is yellow. So you might have seen this obviously within, when you've done some reactions. Cobalt 2+ is a lovely pink colour. Nickel is green. Copper is blue, so copper 2+ is a blue colour. titanium 3 plus is purple, and titanium 2 plus is violet. So you might have seen quite a few of these colours dotted around. There's some specific ones that really you should be probably more aware of than others. The chromium ones, obviously, you will have seen through, like I said, looking at oxidation. You need to be aware of the cobalt. So your cobalt ones, that's obviously going to be quite important. Nickel is going to be quite important as well. Obviously being aware of that. Copper is going to be quite important. So these are some of the colours that you're probably going to see a little bit more often. So these are the ones here. Some of these you might not see as much, like your vanadiums you might not see as much. And iron you might see a little bit of. So just be aware of some of these colours here and just try and remember them. We will go through some of the equations here anyway that you'll probably see quite a bit more. Okay, so we need to be able to compare the properties of S block element calcium with transition elements, okay, in particular. So if we're looking at the properties, we can see that the melting and boiling points of transition elements are similar to each other. However, calcium doesn't really fit this trend, I suppose. So we can see obviously that the ionic radius for calcium 2 plus, let's have a look. There we are. Okay, so there's your calcium 2 plus there, is higher. So the radius is much higher than it is for other transition elements with the same charge. Okay, so if we kind of scan across the side there, and this gives rise to obviously some of these properties as well. So just make sure that obviously if you're looking at calcium, looking at the melting point of calcium, it's obviously a bit lower. When you get into transition metals, obviously these can form metallic bonding. All the way across here, so form some quite big complexes. Obviously the melting point is there, and they're a little bit more dense as well, so they've got a higher density. They can pack together quite a bit more. So it's just really looking at the properties and just being aware that obviously the radius of, say, group 2, so your calcium, for example, the ionic radius is going to be a good bit bigger than it is for transition metals, which generally tend to pull the electrons a bit closer towards them, mainly because you've got an increased number of positive charge, so the number of protons in the nucleus increases, and so therefore that brings that radius in. So it's just a brief look at that, comparing transition metals with an S block element. Okay, so titrations are really important. You would have done quite a few of these practically. Now, transition metals do appear quite often when you're doing a titration. In fact, you might have done them. You might have done manganese, for example. You might have done dichromate reactions. So titrations and transition metals really go together quite nicely. So they can be used to work out the concentration of a reducing or oxidizing agent. And in this example, we're going to look at trying to find the concentration of MnO4-, these are manganate ions, by titrating against a reducing agent a little bit like Fe2+. So here we're just going to look at finding the concentration of a reducing agent. Obviously, if we're going to work out for an oxidizing agent, we just reverse the chemicals, what's in the burette and what's in the conical flask. So in this example, we have a reducing agent. This, for example, is Fe2+. We have that in an unknown concentration, but a known volume. So we don't know what the strength is of it, but we do know how much we're going to put in here. So, for example, it could be 50 centimeters cubed or 25 centimeters cubed, something like that. Will go into the conical flask, but we don't know how much is in there. We don't know the strength of it. So we can add, obviously, excess dilute sulfuric acid into this as well, and this is to ensure you have a sufficient amount of H+ ions to allow this reaction to happen. You'll see when we put our equation up in a moment, it'll be on the next slide where why that's important. So we have an oxidizing agent in the burette. This has a known concentration, so we know how strong this is, and this could be, for example, manganate ions, so MnO4-, which is a good oxidizing agent. So then what we're going to do is we're going to add the manganate ions into the burette, we're going to add it into the conical flask, and we're going to keep adding it until the faint colour of manganate appears, and this is known as the endpoint. So in other words, when you add this in, let's bring this mouse back in. So when you add this in, this will be colourless, and this will be a nice, like a purpley colour, deep purple colour. So when you add this in, this will go colourless. You shake this, and it'll go colourless. As soon as you get a pale, faint colour starting to appear, and it's permanent, even if you shake it, there's a permanent kind of colour that exists there, then you stop titrating and you measure the amount of manganate that you've added to this conical flask, and this is the end point. Now practically when you do this, you add it very slowly as you're getting closer to it, drop by drop. You don't want to go over. So there's a sharp colour change. Okay, so your manganate ions, you've got a sharp colour change basically. So your manganate ions from the aqueous potassium permanganate solution are purple. So a lovely, lovely kind of deep purple colour. They'll immediately react with the reducing agent until all the reducing agent is used up. So you have to be really slowly adding it drop by drop. Otherwise it will basically, you'll kind of add too much into it. So one drop at the end point can turn that solution purple. Okay, and that's what you don't want. If it goes the same color, basically, if this flask is the same color as what's in here, you've probably gone too far. Okay, so it should be a nice pale color. So what we could use is a colorless oxidizing agent and a colored reducing agent. And obviously, what we're doing is just looking for that color to disappear in here. So it could be the other way around. It's just what we're looking for with titrations is a color change mainly. So we're going to read how much oxidizing agent was added. Remember, we've got to read the bottom of the meniscus. So the meniscus is like the little bubble at the bottom of the burette. We've always got to read at the bottom of that. And obviously always read eye level. Now we're going to record our results in 2 decimal places. Okay, always. And repeat until you get 2 results that are concordant with each other. Okay, so when we say concordant, it means they kind of they're within 0.1 centimeters cubed of each other. As soon as you've got at least 2 results that are within 0.1 centimeters cubed of each other, then we can stop, and essentially we have we can be pretty confident that the value that we've got there, it can be used to help work out the concentration of iron 2+ that's in your conical flask, because essentially that's what we want to work out, isn't it? We want to know how much we've got in there. Okay, so like I say, redox titrations, we can use them to work out the concentration of a reagent. So let's put some figures to this then. Okay, so we ran the titration, we've got some concordant results, and we can say that 18.3 centimeters cubed, there we are, of 0.0250 mole per dm cubed of potassium manganate, that's in your burette. That reacted with 25 centimeters cubed of acidified iron 2 sulfate, that's in the conical flask here, and we need to calculate the concentration of iron 2+ ions. So here is the equation. So we've got KMnO4 in here, this is the lovely purple colour, and we've got iron sulfate in here, which is like a very pale green colour, so iron 2 sulfate, like almost colourless to be honest. So here's the first thing we need to do is write out an equation and balance it. So here we've got MnO4 minus, obviously going to Mn2+, and we've got Fe2+, going to Fe3+. And obviously we then have to combine these and balance them with water and protons, etc. Now, you need to be familiar with this bit here and writing out half equations. This you would have seen in when we looked at redox reactions, so electrochemistry, I think in year 1, the electrochemistry topic in year 1, when we look at how you create half equations, combine them to form a full ionic equation. So you're not expected to remember this whole equation here. We are expected to combine, obviously, the manganese half equation with the iron half equation, and obviously balance it with water and protons to form this. So that's the first step, though, is to write out your balanced equation. Now, they might already give you it, but you need to do that. So then we need to calculate the number of moles of manganate, so MnO4 minus. So moles, remember from year 1, concentration times volume. Okay, so the number of moles, obviously put your numbers in there, so it's 0.0250. This is the concentration of manganate ions, okay, because that's what we've got there, multiplied by the volume. We added 18.3 centimeters cubed. Remember, okay, we've got to convert that to decimeters cubed first. Okay, so we divide that number by 1,000. What I've done, I've put times 10 to the minus 3, and that means exactly the same as divided by 1,000. And that gives us 4.58 times by 10 to the minus 4 moles. Okay, so that's the number of moles of manganate that was used, that was added in here. Then what we're going to do is use the equation to find out the molar ratio in order to work out the number of moles of Fe2+. So we know the number of moles here, okay, and we can see we've got a 1 to 5 ratio, there it is, we've got a 1 to 5 ratio of MnO4 minus ions to Fe2+. So therefore the moles of Fe2+ is going to be the moles of that, which is your manganate, multiplied by 5, and that means we have 2.29 times by 10 to the minus 3 moles of Fe2+ ions, and this is what we had in here. Then we need to calculate the concentration of Fe2+ ions, and again from year 1, concentration is moles divided by volume, so the number of moles is 2.29 times by 10 to the minus 3, that's the number of moles of iron, divided by the volume, which is 25 centimeters cubed, that's how much we had in there, times by 10 to the minus 3, got to convert that to decimeters cubed, and that gets us 0.092 moles per decimeters cubed. So this is basically using a titration to work out the strength of this solution here. We can use that by reacting it with something else, using molar ratios, and obviously work out the moles there. So they can also be used to work out the percentage of iron in iron tablets, for example. So let's have a look at an example here. So we've got calculate the percentage of iron in a tablet with a mass of 2.5 grams, which was dissolved in dilute sulfuric acid to give a 250 centimeters cubed solution. 25 centimeters cubed portion of that solution reacted with 12.5 centimeters cubed of 0.025 molar potassium manganate solution. Okay, so let's kind of strip this back a little bit. Okay, so we want to work out how much iron is in a tablet. So iron tablets don't just contain pure iron, obviously. It's an iron compound, and so there's other substances in that tablet. But the tablet itself, so the whole thing, weighed 2.5 grams. We basically dissolved that in sulfuric acid to allow it to, because it just dissolves easier. And obviously we need the H plus ions as well. And we made a massive vat of this stuff. Okay, so we've got a massive vat of acid with the dissolved tablet of 250 centimeters cubed. We then poured some of this big vat of solution out into a 25, or used a burette, should we say, took a 25 centimeter cube portion of this bigger solution, put that in a conical flask, and then this reacted. We obviously ran a burette, ran a titration, and we needed 12.5 centimeters cubed of your manganate, which is in your burette, of this strength to neutralize it, basically, or to react with all the ions that's in there. So the first thing we need to do is write out the equation and balance it. Okay, so in this case, there's your equation. So you've got manganate with your Fe2+. Okay, the next thing, as we've just seen before, we calculate the number of moles of manganate ions. So moles is the concentration times by volume. So the moles is going to work out at 3.125 times by 10 to the minus 4 moles. Okay, it's the total number of moles. So remember, this is the strength. That's what we're being given there. It's the concentration times by the volume that we needed. That's 12.5. But we've got to convert that, remember, to decimeters cubed. Okay, so we'd be given it in centimeters cubed. We've got to divide it by 1,000. So then we're going to use the equation to find out, and the molar ratio, to work out how many iron 2+ ions we had in our 25 centimeter cube portion. So that's in your flask, remember, below. So we know we have a 1 to 5 ratio, okay? So then we can then obviously multiply the number of moles that worked out here by 5, and that means we have 1.562 or 1.5625 times 10 to the minus 3 moles in 25 centimeters cubed. Okay, now what we've worked out here is just a portion of the bigger solution. Remember, we wanted to work out how much iron was in the tablet, and that tablet was added to a massive vat of solution. So we can't just use this to work out how much iron we've got in that tablet, because we've only got a small percentage of that. So what we need to do is we need to work out the number of moles of iron 2 plus in the in the tablet for the whole iron tablet, and we need to know how many moles we had in the original solution that we took from to titrate against. Obviously, you're not going to titrate against a quarter litre of liquid. You need the biggest burette in the world. So that's why we're just taking a small sample, but we do the maths and we scale that up to the original amount that we had there. So naturally, we're going to multiply that by 10. So to work out how much we have in 250 centimeters cubed, which is our initial solution, so we're going to take the number of moles, multiply it by 10, and we get 1.5625 times by 10 to the minus 2 moles. So that's how much iron was in the 250 centimeter cubed solution. Now, what we can do is we can calculate the mass of iron in the tablet that was added to this big solution. So we do mass equals moles times by the relative atomic mass. So here we know the mass of Fe in the tablet, or the mass of Fe in the tablet, sorry, is 1 mole of iron weighs 55.8 grams. So you use your periodic table to find that out. So one tablet contains 1.5625 times 10 to the minus 2 moles, okay, times by the MR, and that's going to be 0.871 grams of iron. Okay, so that's how much iron's in there. And then what we have to do, obviously we don't stop there because it's asked for a percentage of iron in the tablet. Now what we can do is calculate the percentage of iron in this tablet. So the overall mass of the tablet was 2.5 grams. 0.871 grams of that contained iron, which obviously in the iron tablet. So all we do is we take the amount of iron divided by the total mass times by 100, and the actual tablet contains 34.8% iron in that whole tablet. Quite a lot there, isn't it? But hopefully you can see the logic. That's what I'm trying to get at, is you're looking at it's methodical. You can, it's trying to justify each step. Why are we working that out? What's the purpose of that? And hopefully by talking through it and justifying each of the different parts, it becomes a bit clearer. Okay, so we're going to look at a different titration reaction. Now we can apply this same kind of methodology or the calculation to some other ions as well. Now, this is actually just another form of catalysis, which we've seen in the, I think it was topic 26, where we looked at catalysis, and we looked at a bit in year 1 as well. So actually, this is just an example of a very weird reaction that actually catalyzes itself, what we call autocatalysis. But anyway, so aside from that calculation, you need to know the reaction. Okay, so Mn2 plus here is the catalyst in a reaction, and this is going to be between C2O42 minus, and so this is your ethane diweight ion, that's what it's called, and a manganate ion, which is obviously on that side there. So remember, catalyst is always reformed, it's never used up. Obviously we've seen this obviously in the previous topic as well. So Mn2 plus is a product and a catalyst, and this means that as the reaction proceeds, the amount of product increases, and so does the rate of reaction. So it gets faster and faster and faster and faster. It's a bit of a strange reaction, isn't it? So the reaction uncatalyzed is really slow. And the reason why is we're actually trying to react two negative ions together. So you've got the C2H4, so ethane diweight ion, which is 2 minus, with a manganate ion, which has a negative charge. So this means it requires loads of energy to actually force these together. They're just not interested. They're two negative charges. They don't want to be near each other. So it has a really high activation energy. So we need a catalyst to help help this reaction along. And so the first step in this reaction is the Mn2 plus. Okay, this catalyzes the reaction, and it converts MnO4 minus first into Mn3 plus. So the MnO4 here reacts with the Mn2 plus, okay, which is the catalyst, which is there, okay. So that reacts with that, and what it does is it reduces the MnO4, okay, which is this over here, to Mn3 plus. Okay, so you've got your Mn3 plus there, and obviously you produce some water. And then secondly, the Mn3 plus formed, which is this here, then reacts with your ethane diawate ion, which is, and we'll look at this in a little bit more detail, you'll see it as a ligand later, but this reacts with the Mn2 plus that that obviously we have in the solution, the Mn2 plus ions are reformed, so this Mn3 plus reacts with the ethane diawate, Mn2 plus is made back again. That's how we know it's a catalyst, because we started with it there and it's reformed and we produce carbon dioxide. So this reaction has actually produced Mn3 plus. There we are. No, it's actually produced Mn2 plus. There we are. There's your Mn2 plus there, and it's produced your carbon dioxide and it's produced your water. So this reaction, this reaction here has actually worked because the Mn2 plus has effectively kind of split them up into two different kind of steps here. Okay, so we need to know another type of reaction, and there's loads of different reactions here, isn't there? So this is a copper percentage titration. Okay, so this uses iodide ions as we've seen before anyway in previous topics, but copper 2 ions oxidize iodide ions to iodine. Okay, now this is particularly useful because it allows us to find the percentage of copper in an alloy such as brass. So if we've got some, like a piece of brass, for example, we want to work out how much actual copper is in there, we can run a titration and try and work out what we have. So this one's a multi-step reaction. So step 1 is we use an oxidizing agent to oxidize as much of the iodine as possible. So the first thing is we need to dissolve a known mass of the alloy in some concentrated nitric acid. So we dissolve it, pour it into a 250 centimeters cubed conical flask. So it's quite a big flask. Make it up to 250 centimeters cubed with deionized water. Okay. And then we're going to take 25 centimeters cubed of the solution from that flask and we're going to put it into a conical flask. We're going to add some sodium carbonate solution to neutralize any of the nitric acid that we added initially. And we're going to keep adding until we just start to see a precipitate form. Okay. We're then going to add several drops of ethanoic acid and to remove this precipitate. So we're trying to remove that acid from the solution there. So we're just trying to clean it up a little bit. Then we're going to add excess acidified potassium iodide solution, which will react with the copper ions. So that's going to react with the copper ions that's in there. And here's the reaction. So you've got your copper 2 plus ions. Now this was actually extracted from the brass, as you can see from here. So this is the step here. React it with your Ki, so potassium iodide. That's going to provide your iodine. And you're going to form copper iodide and iodine. Okay, so the I minus ions are oxidized to iodine, and your copper 2 plus is reduced to copper 1 plus, and we get this white precipitate of copper iodide that's actually formed. Okay, so that's the first step. So we're using an oxidizing agent, and we're going to try and oxidize as much of the iodide as possible. Okay, so we're going to get rid of as much of that as we can. Okay, so the next step, so step 2, is we then need to work out the number of moles of iodine that has actually been produced. Okay, because this, remember, the number of moles of iodine will help us to work out how much copper we had initially. So we're going to take the product mixture from step 1, okay, and we're going to titrate this against sodium thiosulfate solution, and that's going to use to find the number of moles of iodine present. So remember, the number of moles of iodine the amount of iodine is heavily dependent. Well, it's dependent on the amount of copper that we had initially. Because remember, the iodine was only formed through the oxidation of iodide ions, which in themselves reacted with the copper ions. Okay, I hope you're following this so far. So there's quite a few steps here. So then the step 3 is we're going to calculate the concentration of the oxidizing agent. Okay, so what we're then going to do is work out the number of moles of copper in both the 25 centimeters cubed, so that was in the bit that we've actually titrated, and the original massive vat of 250 centimeters cubed of solution. Okay, so remember to take into account the molar ratio, 2 moles of copper ions and 1 mole of iodine. Okay, so remember that. Okay, now we know the concentration in 250 centimeters cubed. We can then, now we know the concentration 250 centimeters cubed, we can calculate the mass of copper in the original alloy sample. And then the last step is to calculate the percentage copper in the alloy completely. Okay, so let's have a look. Okay, oops, there we are. So what we're trying to do here is look at a methodology, a way in which we can work this out. So remember, from this reaction, we're trying to work out the amount of iodine that was produced. We then titrate that with the sodium thiosulfate, and then from that we can work out the number of moles of iodine that we had present, which we can then work out the amount of copper and then scale that back to the 250 centimeter cubed solution. So it's a very similar reaction. In fact, the methodology is very similar to the calculating the amount of iron in the iron tablet, where you work it out 25 centimeters cubed, use the molar ratio to work out what it is in 25 centimeters cubed, times it by 10 to get 250 centimeters cubed, and then work it out from there. So this is a very similar type of reaction. Okay, so this is with copper. Okay, so let's have a look at some of these errors. Now, the errors obviously with this reaction is we've got to ensure that the starch indicator, so we're adding obviously starch to this to basically help identify the iodine, is added at the correct point. And this is when most of the iodine has reacted. Now, normally we'll see this pale yellow colour that's formed. If this didn't happen, then the blue colour would take a long time to disappear. So you just want to, when it just gets nearly all the iodine, so you've added your thiosulfate in there, you keep adding it, and you get this kind of pale yellow colour that's been formed. We add the starch in there, okay, and then we add it drop by drop until that starch disappears completely, that kind of dark blue colour there. Now we're going to make that starch solution ready, because obviously the starch is going to be as an indicator, so you've got to use it when you're ready to use it. Now copper iodide, the CuI molecule, is really difficult to see the colour of the solution. It's really tough to see that. So we've got to keep the solution as cool as possible. Okay, so the iodine produced in that initial reaction, that first step, can evaporate readily at room temperature. Okay, so we've got to be really careful of that, and that can lead to obviously a false titer, which is not very good. And this happens, obviously the final copper percentage would be too low, and obviously we don't want that. So we've got to try and keep it as cool as we can. And when we're adding our starch indicator to detect the end point, we've got to add it when most of the iodine is actually reacted, otherwise it'll just stay blue for ages, like I say, because iodine reacts with the starch, and that's what gives that deep blue colour. Okay, so we're going to kind of move on now. So obviously a lot of them are titrations and certain reactions. You need to be aware of these particular reactions. That's what the exam board is wanting you to know. So here we're going to kind of look at transition metals and redox potentials. So it's quite a small, kind of a small area anyway. So redox potentials tells us how easily an ion is reduced, which is the same as electrode potentials. So we looked at kind of E0 values. So the least, basically, you don't really need to know a lot about this, to be honest, but so there's not much to kind of really explain about. But the least stable ions have the largest redox potential, and therefore are more likely to be reduced. So you can see here's your kind of redox potentials when we're reacting these together. So here we've got copper 2 plus, it has an E0 value of plus 0.34 volts, and is less stable than zinc, which is here, which has a lower E0 value, or zinc 2 plus, sorry, which is here, which has a lower E0 value here. So we're looking at the stability of these substances here. So remember, these are all these E0 values have to follow a standard set of conditions. So that's what the little naught bit means, or the underground symbol here, so it's theta. Temperature is 298 Kelvin, pressure 100 kilopascals, and the concentration of the ions is 1 moles per decimeters cubed. So there may be a difference in the redox potentials to the standard values seen in the data book. So when you run the practical, you might see a slight difference. Obviously, it depends on the environment the ions are in. So you might not be at standard conditions. The room might be warmer or colder than we think. The pressure might be slightly out from the standard potentials. So just bear in mind that there might be a slight difference there as well. Okay, so your redox potentials are just looking at how stable something is and whether that's likely to happen. Okay, so not much to say on that really. Okay, so we're going to look at d orbitals. Okay, so we need to be aware of the shapes of some of these orbitals here, and there's 5 d orbitals. So remember, when we look back in year 1, there was one s orbital, which is spherical. We then had 3 p orbitals, which are like figures of 8. Well, for d orbitals, we have 5 of them. Now, you've seen SP, S and p orbitals already, like I say, in year 1. Now, just like any orbital, any other orbital, they can hold a maximum of 2 electrons each, and because there's 5 orbitals in total, we can have 10 electrons in the overall d subshell. So here's a diagram of them. Now, obviously you're not expected to be able to write them, draw the kind of diagrams of these, but they have all sorts of these exotic shapes. Now, the top 3, these show orbitals at 90 degrees to each other, as you can see. So these, if you kind of look at these 3 in the top, they're 90 degrees to each other, and the lobes of each orbital are between each of the different axes there. And obviously the axes here tells you where they are. So this is dyz, dxz, and dxy. Okay, so these are the different axes. The other 2 orbitals, these ones at the top here, these show the lobes sitting in line with the axes. And so these are given the names, obviously dx squared minus y squared, and dz squared. So these are obviously sitting within a certain axis here. So obviously all together, so these orbitals here are obviously quite important in terms of how we're looking at d orbitals. I know it says you expect to sketch them out. It's unlikely that you'll be asked to do that, to be honest. You just need to be aware of where these orbitals are and the fact that there's 5 orbitals, and you need to be aware that obviously each orbital can have 2 electrons each, so you can have 10 electrons in total in the d subshell. Okay, so let's start and kind of look into one of the other properties of transition metals, and that's their ability to form complex ions, as we mentioned before. So we need to know what a complex ion is first. Now, the word complex sounds horrendous, and it sounds as though it's really kind of complicated, and it's not too bad. I think there's a lot of colours here and a lot of reactions you have to remember, but the actual kind of design of a complex is not too bad. So a complex ion is basically just a big ion. That's all it is. So a complex ion is where you have a central transition metal ion, and that's in the middle, and it's surrounded by a load of ligands represented by L, and you have loads of dative covalent bonds or coordinate bonds kind of bonding into the middle of the ion there. So the central metal ions there, and the ligands, these are, like I say, represented with L. They have at least a lone pair of electrons, okay, so they must have that. And these basically donate that lone pair of electrons into the transition metal ion, obviously form this coordinate bond, this dative covalent bond. Now, you'll know from year 1 chemistry that these are quite weak as a bond. They're not as strong as a covalent bond, so obviously these can be kind of pulled away quite easily, and that gives rise to quite a lot of different reactions with transition metals, actually, and kind of keeps them versatile. So a square bracket, as you can see, surrounds the ligand, and basically you'll have an overall charge, or you may do, you may not, it depends on what you've got. But the overall charge, if it does, sits in the outside of the square bracket. Now, complex ions, they can come in loads of different shapes as well, and we're going to look at these later. Obviously, this is what we call an octahedral shape, but we'll look at some of the other shapes later as well. Okay, so let's kind of zoom in on that bit of a complex, and we're going to look at ligands. Now, ligands are, a ligand is an ion. It can be an atom or it can be a molecule, but it must have a lone pair of electrons, at least one, okay? Now, you can have monodentate ligand, you can have bidentate ligands, or you can have polydentate ligands, loads of different types. So, ligands which only have one lone pair are called monodentate ligands. Sometimes they're known as unidentate. So, let's have a look at some examples. So, you've got water is a monodentate ligand. So is ammonia, chloride ions, and hydroxyl ions. So these are some of the common kind of monodentate ligands you'll see. Ligands which have 2 lone pairs of electrons are called bidentate ligands. And specific ones you need to know, which you've seen just earlier in this video, ethane dioate ion, which has 2 lone pairs. Also got ethane 1,2-diamine, which is this bit here. So basically it's an amine with a lone pair of electrons, but it's diamine. And then ligands which have more than one coordinate bond are called multi-dentate ligands. So a classic example is EDTA 4-. It's a very big complicated ligand. You don't need to draw it out. But EDTA 4- is an example of a multi-dentate ligand. It can actually form 6 coordinate bonds. So it's a bit of a beast of a ligand, to be honest. It's massive. 6 coordinate bonds, and that can bond with the central metal ion as well. Okay, so obviously we know what some of these ligands are, so we've kind of had an introduction. We will come back to the ligands as well, and you'll see them all the way through. We're just kind of introducing different concepts here, I suppose. Complex shape, that can change as well, and actually that's dependent upon the size of the ligands that we attach to the central metal ion and the coordination number. Okay, so the coordination number is the number of coordinate bonds. Okay, it's not the number of ligands. So for example, EDTA is 1 ligand, but it has 6 coordinate bonds in the middle. So it's the coordination number for that complex would be 6, but we've got 1 ligand. Okay, so remember, coordination number is the number of coordinate bonds. So some ligands are small, and actually you can fit 6 of them around a central metal ion. So you've got water, you've got ammonia, and you've got hydroxide ion. So I kind of imagine this a bit like pigs around a trough. So the trough is like the metal ion. Okay, it's in a fixed position and it has a certain size. And if you've got little pigs, you can fit loads of little pigs around that trough and they can all get to the food quite easily. But if you've got much larger pigs, so this could be like Cl- ions, for example, they're a bit fatter, you can't fit as many of these pigs around the trough. There just isn't enough space. So larger ligands like Cl- ions, you can only fit 4 of them around a central metal ion. There just isn't enough space to put 6 of them around, like water, ammonia, and hydroxide ions. Ethane diuate and ethane 1,2-diamine are even bigger than chloride ions, and normally we can only fit 3 of these around a central metal ion. So obviously these are a lot bigger, and obviously they bond twice each anyway. Okay, and let's have a look at some of the names of some of these then. So complexes with a coordination number of 6, so they've got 6 coordinate bonds. These form octahedral shapes. So you can see here we've got an example. This is cobalt, and it's surrounded by 6 water ligands all the way around. And this has got an overall charge of +2. It's also written as this. So it's cobalt with a square bracket, water, obviously 6 waters, and 2+ charge. So cobalt with your ammonia, you've got obviously 6 ammonia ligands going around it. Cobalt in the middle, again 2+ charge. And this can also be written as cobalt 6 NH3, so there we are, with 2+ and aqueous. So that's how we can write them as well. So all the bond angles in this, in anything with 6, which can fit 6 ligands around, so these are smaller ones, these are all 90 degrees. So again, this is going back to the bonding topic in year 1, where the obviously bond angles are determined on the shape of it. So this is an octahedral shape, no difference to what you've seen in year 1. Okay, so complexes with a coordination number 4, these form tetrahedral and square planar shapes. So here's one here. So this is copper chloride. So remember your chloride ligands were much bigger. You can't fit as many of them around. So copper chloride, CuCl4, you've got 4 ligands around here, and these obviously form a bond there. Also written as CuCl4 2-. The bond angles in tetrahedral, if you can remember from year 1, are 109.5 degrees. And here's another example. This is another example of a square planar. So this is platinum with ammonia and 2 chlorines. And this is also written as this. So basically we have the square brackets. We have 2 ammonia ligands and 2 chlorine ligands in that complex there. And a specific example of a square planar is an anti-cancer drug called Cisplatin, which you do need to know that as a specific example of a square planar molecule. There's very specific ones really here. And the bond angles obviously in a square planar complex are 90 degrees. Okay, so complexes with a coordination number of 2. So these form linear shapes, and a specific example are some silver complexes. So here's a classic example here. So this is silver with 2 ammonia ligands surrounding it. So AgNH32. Again, this is just a specific example you do need to be aware of. Okay, bond angles in linear compounds are 180 degrees. Obviously, that's between them points there. And this is known as Tollens reagent, and you've seen this before. So AgNH32. Okay, so as you've seen before, another feature of right now complexes is they have an overall charge. And this is basically the same as its total oxidation state. So the total oxidation state of the metal, okay, equals the total oxidation state of the whole complex minus the total oxidation state of the ligands as well. So let's look at this example here. We've got copper with 4 chlorine ligands or chloride ligands around it. Overall charge of -2. Okay, so that's the total charge of the whole complex. Now each Cl- ligand has a charge of -1. So there's 4 of them in total. So that means we have a total oxidation state for the ligands of -4. So that must mean the total complex oxidation state is -2, because obviously that's what we've looked at there. And so therefore the oxidation state of copper in the middle has got to be +2. So that's +2 there, and you've got 4 minuses around there, so that gives you the overall charge of -2. And it's as simple as that. That's how we work out the oxidation state of copper that's in the middle. So relatively straightforward. Okay, so kind of looking at so we're going to look at the kind of orbital level a little bit further, and looking at the orbitals with the shapes that we've just seen there, and we need to understand about d-orbital splitting. Okay, now this can be a little bit tricky, this bit here, but the d subshell is split into 2 when ligands bond with the central metal ion. Okay, it's a bit weird this. Okay, so let's have a look at this in a bit more detail. So we've got the 3D electron configuration for cobalt 2+ ion, so CO2+, when no ligands are attached to it. So it's just the ion. Imagine it has no ligands around it at all. That's the d orbital. When we attach ligands to this ion, though, some of the orbitals gain energy, and we get an energy gap that's created, and this is what we call delta E. So this is, for example, cobalt with 6 waters around it, so this is hydrated. Now, the d orbital splits into 2 parts, so you've got some electrons in here and some electrons at the top, and we create an energy gap here, which is also known as delta E. So what happens is when electrons absorb light energy, so in other words, you've got a beaker, you put it on the windowsill, and obviously it'll absorb the light energy from obviously the window. Then some of the electrons move from the lowest energy state, which is called the ground state, okay, to an excited level called, or higher energy level called an excited state. So there's your light energy there, because your light energy's gone in, and it's moved one of the electrons into the higher state there. So you can see there's the electron there. That's now flipped and gone into the upper orbital here, and that's been absorbed by light energy. So this is the excited state, this bit here, because we've got an electron there. Now, in order for this to happen, the energy from the light that's obviously been absorbed must equal the energy gap, that's delta E. So the size of delta E, the size of this gap here, is dependent on the central metal ion and its oxidation state, in other words, what we have. It also depends on what ligands we have bonded to it. In this case, we've got water, but you might get different energy gaps. Use chloride ions, for example, and the coordination number, hence the shape. So this is obviously an octahedral d-orbital splitting, and this is where we get 3 orbitals at the bottom and 2 at the top. Now, when we form a tetrahedral complex, we get exactly the same. We still get d-orbital splitting, but they split slightly differently, and actually we have 3 orbitals at a higher energy and 2 that are lower down. Okay, so let's have a look. This is the cobalt one, exactly the same example as what I mentioned before. But actually, when we react it with, say, when we have a tetrahedral structure, so we have 4, coordination number 4, so we have COCl4 instead, then actually the splitting kind of flips the other way around. So with the octahedral structure, we had 3 at the bottom, 2 at the top. Here we have 3 at the top and 2 at the bottom. So we've got a slightly different setup here. Okay, so we still have an energy gap that's created, so the principle is the same. And obviously when electrons absorb that light energy, some will move from the lower energy state here and will move to a higher energy excited state. So you can see here we had 4 electrons in the bottom. We've now got one of the electrons has migrated up into the top here, and obviously light energy has been absorbed at this point. So you can see this kind of splitting of the d orbital, this kind of unique property of d orbitals in terms of this, or transition elements in particular, is that actually they can split depending on what they're bonded with, the type of ligands and the type of metal that you've got. And you can now probably, if you're kind of one step ahead here, you're probably getting to see why we have so many different colors with transition elements. Because when you absorb light energy, okay, and then some of these electrons will drop back down to their original state, they'll release some light energy. And depending on obviously the size of this energy gap will depend on the color that you get. And obviously this is dependent on loads of different factors, such as the type of ligand, the shape, the type of metal that you've got, and all of a sudden you've got a whole library of potential different colors that could be produced from this. And I hope it kind of comes back to it as well, that actually this is why you need partially filled D subshells to get these colors, because if all of these were full, like for example with zinc, then you won't be able to get any of this migration of electrons, and so therefore you won't actually get any fancy colors. Okay, so let's have a look and kind of delve a little bit further into colored complexes. So some frequencies of visible light, these are absorbed by transition metal complexes, and the frequency absorbs, obviously, like we said, depends on the size of delta E. So you can see we've got our kind of spectrum of color here. So you've got red, orange, yellow, green, blue, indigo, and violet all the way across here. And this is obviously what makes up white light. Now, the larger the energy gap, delta E, that we'd seen before, the higher the frequency of light that can be absorbed. So this is kind of at the top end here. Now, this is what's actually absorbed. Any frequencies which are not absorbed, okay, are reflected, so they bounce back, or they're transmitted. In other words, they go straight through the kind of test tube. So the combination of all of these frequencies, okay, these ones here, they create a complementary color. And that's what we observe. That's exactly the color that we see. So when you see these reactions, you hold up the test tube, you get all these lovely different colors. We're seeing a mixture of the colors that have not been absorbed by the solution. So, for example, copper and 6, so hexa-aqua copper complex, try to say that one quickly, that absorbs frequencies that produce red light. Okay, so that absorbs that, and the complementary color, and this is your color wheel here, is light blue or cyan. And actually, when we look at hexa-aqua copper 2+, we do see a pale blue solution. So it's absorbing this red, but obviously the mixture of all the other colors will produce this kind of cyan color here, which is this pale blue. So that's the complementary color. And so for those complexes where we have a full or empty 3D subshell, this is what I was saying before, you have no electrons can migrate to these higher energy levels, and this means we just see these as white and colorless. So this is like scandium and zinc, for example. Okay, so like we say, the size of delta E is dependent on the types of ligands, and we're going to explore some copper complexes with water, ammonia, hydroxide, and some chloride ligands. So we're going to look at various different types here. So the order of ligands which cause the most amount of d orbital splitting is shown below. So as we go down the list, the splitting of the d orbital increases. So we've got ammonia is right at the bottom, that increases the kind of gap. Chloride ions don't increase that gap as much. So as the splitting increases, okay, so as we go down the group, the light absorbed will shift more towards the violet color. This is what the complex absorbs. Okay, so it needs more energy, remember. So CuCl minus, CuCl4 here, 2 minus, absorbs frequencies that produce blue light. Okay, so remember that the splitting isn't as great here, so it'll absorb kind of the yellow color, so a little bit lower down. Okay, it absorbs the frequencies that produce blue light, so it's kind of up here. The complementary color is yellow, so that's the color that we observe with that one. If we look at hydroxide ions, some hydroxide and water, this absorbs frequencies that produces the red or magenta color. So the complementary color is green. So we get this greeny color here. And then for the copper with just the water, so just the pure water, this is the one down here, this absorbs frequencies that produce red light. Okay, so the complementary color is light blue or cyan, so that's what we see there. And then finally, with the ammonia ligand in there as well, this absorbs frequencies that produce yellow light, and the complementary color is dark blue, and that's the color we observe. So what we're trying to say here is you get loads of different colors that are produced, and the colors that are produced is dependent on the ligands that we have, the type of ligands, and obviously the metal ion is staying the same, but we're just changing the ligands, and with the chlorine one, we're changing the shape as well. So you can see this is why you get this variety of different colour, loads of different colours here. Okay, so let's have a look and move on to isomerism, because transition metals can form isomerism as well, in particular optical isomerism. Now, you've seen this in year one, so we're just kind of dragging some of the information from year one and applying it to transition metals. So complex ions, they show optical isomerism, and this is a type of stereoisomerism. So remember, complexes are optical when they are not superimposable. So if you'd seen the previous video for year one, I had my hands out and I was overlapping them and trying to turn them over each other. Anything that is non-superimposable isomers, which are non-superimposable, will be optical isomers. So they're mirror images of each other. So you can see with this complex here, we put a mirror line down the middle of this, and they are definitely optical isomers because they're mirror images of each other. And so therefore, octahedral complexes with three bidentate ligands, these show optical isomers like we can see the one on the left. So you just need to be aware really in this example here is that transition metal complexes can form optical isomers, and just be prepared to be able to draw out the mirror images of these isomers as well. And obviously they have the same behaviors as them. So anything that's optically active will rotate plane polarized light as we've seen earlier. Okay, and complex ions also show cis-trans isomerism, which is another type of stereoisomerism. So this is a branch of EZ. So your octahedral complexes with 4 ligands of the same type and 2 ligands of a different type, these display your cis-trans isomerism. So you can see here that we've got 2 chlorines obviously in the polar regions. There we are, so right top and bottom, with your 4 water molecules kind of in the square planar arrangement. Whereas with this one here, the 2 chlorines are within the square planar arrangement, and then you've got your 2 water ligands that are in the axial positions at the top there. So there we are. So if the 2 different ligands are opposite each other, see the ones on the left, this is trans isomer, so obviously they're opposite, so it's trans cobalt complex. And if they are on the same or they're adjacent to each other like we see there, then this is a cis isomer. So just be aware of these different types of isomerism in complexes as well. Okay, so just a kind of reminder, this is what we call a non-polar molecule. Okay, so this one here. So the chlorine ligand is the most electronegative out of these ones, but they cancel out because they're opposite ends of the complex. So this is a very symmetrical complex here. So this is non-polar when we're looking at the polarities of this. Whereas on the other hand, this one is a polar molecule because the negative of the Cl- ligands are all on one side of the complex rather than kind of spread equally. So this is a polar molecule. So just be aware that you are expected to kind of discuss polarity of complexes as well. Okay, your square planars, they also show some cis-trans isomerism. So you can see here, this is cisplatin. This is your one of them is anyway. It's an anti-cancer drug. That's cisplatin. So let's have a look at them in a little bit more detail. So this one is transplatin. So if you've got two ligands that are opposite each other, as you can see there, so they're opposite the platinum, okay, and vice versa with chlorine, then these are trans isomers. And then if you see on this side, this is a cis isomer because the ligands are on the same side, okay, of the platinum. There's chlorine and ammonia, and they obviously can't move. So this is a non-polar molecule because we've got an even distribution of charge across the molecules, so they're on opposite sides. Whereas this one is polar because the chlorines, let's say, because these are electronegative, they kind of sit on one side of this complex here, so therefore it's weighted to one side, so it is a polar molecule. Okay, so we've kind of seen a little bit of cisplatin there. Now, cisplatin is an anti-cancer drug. It's a square planar complex. It has the platinum metal ion in the middle. It has two ammonia ligands and two chloride ions, as we've just seen before. So cisplatins are really, obviously, it's a really important chemical, especially used in medicine. It's used as part of chemotherapy. And what cisplatin does, it binds to the DNA in cancer cells. So these chloride ions in the complex, they're easy to displace, they're easy to break off, and they can detach from the complex, and then this can then bond to the nitrogen atoms in the DNA in a cancer cell, for example. And obviously, because this complex is obviously attached to the DNA, it stops that cell from reproducing. Now that cell is a cancer cell, and we don't want that to reproduce and spread. So we want that cell to just die, and it's unable to repair itself. And that's the idea with drugs like cisplatin. The issue, though, and obviously if you know anybody, or if you have yourself in the unfortunate position to obviously suffer cancer, what we do know is actually, especially with chemotherapy, that it does destroy, or it can destroy healthy cells at the same time. So, for example, it affects cells in the blood, which can suppress the immune system for somebody who's perhaps going through chemotherapy, and it can risk the infection and potentially kidney damage. So, some people may have a side effect where they may lose their hair as well because it destroys some of the hair cells. So, chemotherapy is obviously very important. It can help to target cancer cells, but it does target healthy cells as well. So obviously scientists are putting an incredible amount of research in to try and develop drugs which are more specific. So they target particular tumours and target the cancer cells rather than having these quite nasty side effects, really. I mean, I suppose, they are. I mean, I'm fortunate never to have cancer, but, I can imagine that there isn't really too much of a choice if you want to try and destroy the cancer cell. So, but it's quite a rough journey, for many people. But these drugs have saved millions of lives globally, so they are very, very useful, as you can see. Okay, so we're going to look, I suppose, towards the kind of back end of this video now. We're kind of moving towards the end of it anyway. We're going to look at some substitution reactions and look at some of the colours that you need to be aware of. And then we're going to look at stability constants, so case stab towards the end. So, a colour change can exist, and we've seen a lot of these colour changes and why these things are coloured, but we need to know about some reactions as well. So, a colour change can exist when ligands in a complex exchange or substitute. Okay, so these substitution reactions show ligands of a similar size being exchanged. So we're swapping kind of like for like, but changing the ligand. So here we've got cobalt with water. This is reacting with ammonia, as you can see on here, NH3, and this will form a hexa-ammonia cobalt complex, and the 6 waters are kicked off. So this is an example of a substitution reaction. So we've got a pink substance here. This is obviously octahedral, and we form a straw-coloured, and again, still octahedral shape here. So both the ammonia and water are obviously similar in size, as we've seen before. So they've got the same charges, they're both neutral, and so the complex shape remains octahedral. We've got a colour change though because the ligand has changed. So if we look at copper, So copper here, we've got 6 water ligands here around copper, but the amount of ammonia that we've got is obviously not, is only 4, and we form this complex here. Now it's blue to start off with, and it's a dark blue on that side. But you'll notice with this reaction in particular, there's only a partial substitution, okay? We don't get a full substitution here. So this reaction occurs when we've got copper H2O6 here. This reacts with excess ammonia. So when we've got loads of ammonia, we will get the maximum substitution that we can, which is here. These bonds are just a little bit too strong. The water copper bonds, the polar bonds, are a little bit too strong for ammonia to break them off. So these kind of remain stubbornly on the complex. So we get this partial substitution here. So just be really wary of that. Okay, you do have to remember that. Okay, so let's look at the same thing, but the substitutions, we're going to show ligands of a different size being exchanged in these examples. So remember, Cl- ion is a larger ligand than water of ammonia, so we can only fit 4 chloride ion ligands around this shape. So we do have a change in shape and coordination number. Okay, we're going to look at some examples here. So there's your cobalt H2O6. We've got 6 water ligands around cobalt. Adding a chloride ion in there, that'll form copper chloride and 6 waters. Now here we're literally going from a pink to a blue colour, but what we're doing, so what we're doing is basically kicking off all of the water ligands here, displacing them completely. So displacement's a better word. So we're displacing these water ligands here, replacing them with chloride ligands, and we're getting a very different complex. So here's copper H2O reacting with 4 chloride ions. So this is obviously copper rather than cobalt. Again, we're going from blue to a yellow colour, and we're going tetrahedral. So the shape is actually changing here. And here's iron, again, adding chlorine. We're going from yellow to yellow. So the colour is actually pretty much the same. There's no difference in colour there. But it's about commenting obviously on the shapes of these as well. Okay, so let's look at a bit of a like summarizing, I suppose, some of these. So we're going to look at some complex ion solution in colors. So metal ions dissolved in water. Okay, so these only have the formula of that. Okay, so it's metal with H2O6. What I've done down here, okay, is I've simplified that to Mn+, and you'll probably see it here. So we're going to look at the kind of reaction changes when we add it in aqueous solution, okay, and then when we add some OH- ion or NH3 to aqueous solution, when we add excess to it, and then when we add excess ammonia as well to the precipitate. So let's have a look. So copper, when we react copper in water, obviously we form CuH2O6 and it's a blue colour. Iron is pale green. Iron 3+ is a yellow colour, and cobalt 2+ is pale pink, as you can see there. So these are, when we add it in water, you have 6 water ligands surrounding it. So when we add some hydroxide, so just a small amount, or ammonia to this solution, what do we get? Well, in this case, if we add a small amount to copper 2+, we get a pale blue precipitate, and you can see we get 4 water ligands still attached, and 2 OH2, so it's a solid. This overall has a charge. Any complex that has a charge will always be aqueous, okay, so it'll always be in solution. If it doesn't have a charge, like here, because the ligands are obviously cancelling out the overall charge here, then it will form a precipitate, okay, so just a tip, just to watch out for that, okay. So this doesn't have an overall charge, and so therefore as a solid, it's a precipitate. Iron, again, we need to add some hydroxide ions. We've got 2 OHs there, and we've got water ligands, so just enough to form that precipitate. So if we add a small amount, we'll get a precipitate. Again, it's got no charge. With iron 3, we need to add a little bit more hydroxide ions in there, or ammonia. And obviously this is going to form an orange precipitate, so we get OH3. H2O3, so we just need a little bit more than what we do up here, but nonetheless we're still forming a precipitate. And then cobalt, again, we form a blue precipitate here. So if we take these then, okay, so we've added like drop by drop, small amounts, got a lovely precipitate. If we then kind of go all out and say, right, we're just going to add loads of hydroxide to this, what do we get with these reactions? So this one is insoluble, okay, in excess. So basically nothing happens. We can add loads of hydroxide and we've just got this. It doesn't do anything. The next one is also insoluble. Again, no change. That's all we produce. The next one is also insoluble. We don't actually get any difference here. And cobalt is also insoluble. So basically we get no change when we add excess hydroxide to any of these precipitates. So let's do the same then. So we've done that. I think, right, well, that hasn't worked. So let's say we get this pale blue precipitate, and now we're going to add excess ammonia to it instead. What do we get? Well, here we do get a change, okay? Actually, instead of just forming an OH2 here, so basically the ammonia is just taking a proton off the water molecule. This was a water ligand, and we've just taken a proton from it. What actually happens is we get a substitution, okay? So we get part ligand substitution. It basically replaces all of the ligands. It goes in, pushes them all out of the way, or most of them anyway, leaves 2 water ligands to one side, and basically boots off 2 waters, 2 hydroxide ions, and replaces it with ammonia ligands. And we get this dark blue solution. It's aqueous again because we've got a charge, okay? Remember, we've got a complex with a charge. It's always in solution. It's insoluble. Iron 2 is insoluble in excess ammonia, so it's not that powerful. Also insoluble in iron 3. With cobalt, it does continue further. So cobalt, here's your precipitate here that's formed. If we add excess ammonia, it kicks off all of these ligands here, and we have 6 ammonia ligands attached to it. We get a brown-yellow solution that's formed, so it's aqueous. Okay, so let's have a look at some of these equations that's involved here. So copper 2+, so copper 2+ reacting with hydroxide ions will form this. So this is a small amount of hydroxide ions. Okay, this is some. And with ammonia, effectively the ammonia is picking off some of the protons from 2 of the ligands here to form OH2. And obviously you get 2 ammonium ligands, or 2 ammonium molecules, should I say. And then if we add excess hydroxide or excess ammonia, it's insoluble for this one. But for this one, obviously it forms, we go from this and it forms this. Okay, so we basically get a ligand substitution or partial ligand substitution. Now with iron, obviously we add a small amount of hydroxide, a small amount of ammonia, and obviously these are the reactions here. So we are substituting, we're taking a proton from the 2 protons from here to form OH2. Same with the ammonia. And obviously if we add excess, they're insoluble for both, so there's no change. Iron 3+, again, a small amount will produce a solid precipitate, as we can see there. So that's the small amounts. And obviously they're insoluble for both of them at the other end. Cobalt 2+, again, adding small amounts of each of them, we'll get this solid precipitate. So we get a precipitate. The precipitate will dissolve when we add excess ammonia. So this obviously forms cobalt hexammonia. So we get full substitution. So all these ligands are removed and we get that's produced, and it goes to aqueous solution. Okay, so kind of looking towards the back end then, we need to look at some stability complex, or K-stab. Now, some complexes are more stable than others, and we can obviously quantify their relative stabilities using an equilibrium constant. And obviously we've seen a lot of these, haven't we? So we know that ligands can be substituted for other ligands, and we've seen that all the way through this topic. And they can do it one at a time, or until most of them are replaced. So the overall equations, let's look at iron and copper, will show this. So you can see here we've got iron obviously reacting this time with a cyanide ligand here, and obviously it removes all of the water ligands, and you have 6 cyanide ligands attached to it. Or you've got your diamine here reacting with copper hexaaqua complex, and obviously you've got 3 of these ligands attached to it and 6 waters. So we can represent the stability of this, or the K-stab expression for Fe3+, for example, if we use this as an example, by doing this. Now, we don't include water. Water is excluded. So we put product, which is FeCN6 3-, over the reactants, which are these here. And that's obviously the expression that we use to represent K-stab. So the size of K-stab, that tells us how stable a complex is. And quite simply, the larger the number, the more stable it is. So let's have a look at some examples and see how this actually works in practice, because it's obviously going to dictate certain reactions and why we see certain reactions anyway. Okay, so let's look at the reactions of copper 2+ complexes and ligand substitution reactions that they can undergo. So we're looking at the relative stabilities of complexes formed by reacting hexaaqua copper ion with ammonia and hydrochloric acid. So we actually form two products here. So we've got 1 times 10 to the 1 times 10 to the 13 for this complex here. So this is with 2 ammonia and 2 waters. And then we've got copper chloride, CuCl2- is 4 times 10 to the 5. So clearly this complex here with the water and the ammonia is more stable than the CuCl2-. So these Cl- ions, remember, these readily substitute all of the water ligands, and it creates this pale blue solution that we can see here. But obviously that is more stable. Now, if we then go and add more water to this equilibrium, so we're going to add more to this, then equilibrium will shift to the left. It'll move to this side because it'll try and use up the water that you've added in. Now, what we will see is we'll actually see we'll have more dark green, a more dark green color, because we're producing more of the copper hexaaqua ions that we'd seen before. So we will get a color change. And then if we look at the reaction with ammonia instead here, so this is obviously the reaction with ammonia, we get this partial substitution as we've seen up here. Now we get this. Now this is more stable, as I mentioned before, than the copper chloride. Okay, so if we add more water to this, okay, it will not shift equilibrium left. It won't actually move it back to here. And this is because this complex, what it's formed here, is so stable. It's almost like stubborn, I suppose. You could call it K-stubborn. So effectively, this complex here is so stable, even if you add more water, it isn't going to break apart to form this, because that's just weaker. So, the kind of forces of stability kind of keep this equilibrium well over onto this side, and we get this nice stable complex. So with this one, adding more water will break this apart to form this, because the K-stab is not very high. But with this one, because K-stab is so high, adding more water to this won't shift it that way. Okay, so let's look at competing equilibria. So we're going to add an extra layer of complexity through this. And this may well occur through, like, say, ligand exchange reactions. So let's look at the hexaaqua copper complex, okay, which is this one here. Okay, and we're going to add concentrated hydrochloric acid to it. So that's going to provide us with the 4Cl- ions. And we form CuCl4-, 2-, and 6 water ligands. Now let's assume that we're going to add to this reaction some concentrated ammonia solution. So now we have another equilibrium that's at play. So we've got the copper hexaaqua ions that are already in there anyway, the ones that still exist. React that with some ammonia, okay, concentrated ammonia, and we form this complex here, okay, and water. Now, as the first equation, okay, so the first equation is CuH2O6. Okay, so this one here, this obviously produces, there we are. Yeah, so the first equation, so this produces CuH2O6 in the reverse direction. Then the ammonia, okay, will actually react with this, okay, to produce more of the stable complex of this. So the ammonia here is going to react with the CuH2O6. Remember this one here, okay, is more stable. This complex is more stable than this complex here. So if we add ammonia, ammonia is going to react with this. equilibrium is going to shift backwards to form more of this, to replace this, and effectively, overall, you'll get more of this complex here because it is a lot more stable than that one up there. So we've got two kind of complexes at play. So as ammonia, like I say, it reacts with the CuH2O6. Equilibrium at the top shifts left to replace this. And this means we'll have less of the copper chloride. So it's like bullied its way through. And this has been dismantled to feed this reaction to produce this, which is a lot more stable. So why does it happen? Well, like we say, we know that this is obviously more stable than that one. And so this actually wins out because the K-stab is higher. So there is an awful lot in that topic. Like I say, it's one of the bigger ones that you'll see. So that's obviously the end of this topic. You'd be pleased to hear there's a lot of reactions in there. Make sure you kind of familiarize yourself with it. Like I say, the full range of A-level videos from topic 1 all the way through to topic 37 is available on Allery Chemistry. All I ask is you hit the subscribe button just to show your support for this project. That'll be absolutely fantastic. Also, these are available to purchase. I've got the full range of A-level notes, which you can purchase from the TED shop. If you click on the link in the description box below, you'll be able to get a hold of them there. Great for adding into your file and writing notes on. Yeah, go and have a look. Right, that's it then. Bye-bye.